Good morning, everyone, or good afternoon, I should say. Today, I'll be presenting on some work that's a little bit of a different venture for our lab here. So we do run a cell mechanics lab. What I'll present on today is some, part of the data from a project that we've been working on for a little bit of time here, where we're really interested in looking at machine learning to predict the biomechanical responses of cells here. Oops. So I want to start off by just acknowledging or just want to do something different this time and just thank my funding sources, thank all the members of my lab, and specifically thank two of my students. They're actually former students now who played a big role in just the data and analysis of this project. So I just want to take a moment to acknowledge Miku, who he's actually doing a postdoc at Georgia Tech. He did a lot of the experimental data gathering, and Vignesh, who recently graduated as well here, did a lot of the analysis and machine learning aspect of this project here. So I want to start by just doing a quick recap for those of you all that saw my presentation about a year ago. Maybe it's been over a year now. My little spiel on the mechanical forces that cells generate. And I wanted to put this up just to do a recap and remind everyone again, or refresh their memories for those of you all that saw it. So the two major forces that we deal with or that we talk about, especially in this presentation, tractions, which we measure using a method called traction force microscopy. And the tractions are going to be those forces between the cell and its underlying substrate. For cells within the monolayer, they're going to generate intercellular stresses. These are the mechanical stresses between cells here. We use monolayer stress microscopy for that. And I have in the upper right corner here just a little schematic of what that actually looks like. So with our method, without going into extreme detail, we can calculate the normal and shear intercellular stress. We can calculate magnitude or orientation, right? And we do time-lapse microscopy routinely as well here. And we can do the same for the tractions, okay? And again, you all may have seen this as well, but I always like to describe tractions and intercellular stresses as we have these guys here playing tug of war, right? And the tractions are gonna be that force that's being exerted as you're pushing down on the ground. And you could think of the intercellular stresses as the tension in the rope. Now, with that being said, where does machine learning come into play here? What's the point, et cetera here? So where this really came into account from a earlier project that my student Miku had actually did. And the idea is that we, at this point, we can quantify, calculate the mechanical forces, subsequent mechanical stresses generated, but it's not necessarily clear how they're generated, right? What are the biomolecular players, so to speak, here, right? And we can do knockouts, we can do pharmacological interventions. And for the early project that one of my students did, we essentially looked at how the mechanical forces cells generated changed in response to various drug concentrations. And the idea was that, well, what if we can kind of cut down on our experiments and actually, predict, a dose response, right, of how cells respond mechanically, meaning I'll take drug A, right, and drug B, right? We don't know what drug is going to cause a minimal or maximal response as far as their ability to exert mechanical forces. And the idea is if we can predict that, in addition to saving time and money, this has some real usefulness in the biomedical field here, because although I showed in the previous slide, yes, tractions are, the forces generated between substrates, and intercellular stresses are going to be between the cells. Tractions are literally a metric of cell contractility. So how hard or soft a cell is actually pulling, right? Intercellular stresses are a metric of cell-cell adhesion, okay? So depending on if they're weak or strong, that'll give you an idea of tissue integrity, for example, here. But the idea is that we actually use MATLAB to do this. The MATLAB has a machine learning toolbox. We use actually quite a bit. We tried quite a bit of machine learning models, but the ones that I'll show today are from results from the stepwise linear regression model and a quadratic support vector machine model here. And the idea is we essentially wanted to predict, how the mechanical forces would actually change in response to drug concentrations. Now, the data from this were done from experiments that I have referenced here, Islam and Steward, in 2018. So the idea is that we took data from, unpublished data from that set, fed it into our model, built the model essentially. Then we wanted to see if we can really predict, how those forces would actually change in response to, this drug that I have here, Calcone. This drug is a berry disruptor and something that we've actually published here as well. But continuing on here, what were the predictors that we used? So we started off with something very simple. So Calcone concentration or drug concentration, monolayer area, monolayer perimeter. And the idea is that, well, with these simple inputs, right? Because the question was, can we take an image of a monolayer, right? And put in a drug concentration, and will that tell us, will the forces increase or decrease, for example, here? So at the bottom, we have a typical image that we get. We have a phase image of an endothelial monolayer, and essentially we turn it into a binary image, and we can extract area and perimeter, and we can put in a drug concentration, okay? And then we ran experiments, and we actually will know what the intercellular stresses will be and attractions actually as a function of various drug concentrations here. Now, one subtle or maybe not so subtle detail here that I'll point out. So we tested two different conditions here, or two different drug concentrations. So what I have, 0.2 micrograms per milliliter and 2 micrograms per milliliter, and this is of that drug Calcone. These were the actual experimental data sets that we fed into our model. Now, what we did after that was actually predict what this response would be for a control or zero concentration of that drug, or 0 micrograms per milliliter, and 1 microgram per milliliter of that drug. And we predicted it with our model, and then we did also run actual experiments to see how our output, how our data from our model actually stacked up against the real experiments here. Now you'll notice as well as we did a time lapse, okay, for 6 hours, images taken every 5 minutes. And how we generated our data set was essentially we, collapsed all the data together, meaning we essentially just averaged it. We built what's called a master table and actually fed that into our machine learning model here. So just a little bit more detail of what that all looks like here. So I kind of moved through quickly in essence of time here, but essentially the idea on this right-hand side here, we have these large tables and we have our predictors, area, perimeter, Calcone here, which is a drug concentration, and we'll get this response. And that response is actually the principal stresses, so we can generate the maximum minimum principal stresses, and from that we calculate our maximum shear stress and average normal intercellular stress here. But let's go on to kind of the data here. So what were the outputs? Okay, so what we see at the top here, we have normal stress and maximum shear stress. The gray bars are going to represent the experimental data, right? The yellow bar and the blue bar are each going to represent predictions from that model using that stepwise linear regression and that quadratic support vector machine learning model, okay? The bottom two bar plots here, we see we have a 0 and a 1 microgram per milliliter concentration. Each of these concentrations were actually predicted from the model. However, you'll notice that we have a gray bar for each of these, which represents our experiment. A note about this is that, yes, we have experimental data from each of these concentrations, but The experimental data from the 0 and the 1 microgram per milliliter were not fed into the model. So these are all just predictions with just the top 2 concentrations that we have at the top here. And what I'll go through quickly again, beyond just bar plots, right, we can actually plot the distribution. So what this is showing again here is, our experimental, data that we actually fed in, our outputs from our 2 different machine learning models that we use. So we have 0.2 and 2, 0 and 1 microgram per milliliter here. And again, keeping in mind that 0 and 1 microgram weren't fed into the model. And here we just have plots. We have what our R-squared value was. The stepwise linear regression model ended up giving us, not the best R-squared, so certainly more work to be done, but better, than, the support vector model that we used here. And let me just kind of, results of what I've showed here, but let me skip to the conclusion. So kind of, final thoughts about what we've done thus far. So, some critiques, we only looked at area, perimeter, drug concentration, right? And each of those data sets were an average of just 4 islands per drug concentration. So the idea is that certainly we believe adding more predictors to calculate our mechanical stresses will certainly improve the data model. But beyond just predicting how drugs change as a function of, mechanical stresses change as a function of drug concentration, the idea is that this could, we believe, I should say, this will actually have implications in the sense that, we can minimize the experiments needed. We can predict dose responses of cellular behavior to various drugs here. And again, this is predicting that biomechanical response, meaning, we can get a library of drugs, and this is a 10 years down the line thing anyway, but we can look at a library of drugs, right, screen them, apply our model, and really determine or try to tease out a concentration that will give this maximal response of cellular contractility or cell-cell adhesion forces here. But with that being said, I'd like to thank everyone who stayed for attending, and I'd be happy to answer any questions that you have.